Swayam Prabha. Digital India. Educated India.
This maritime engineering, as you see, is a very special program which has got multidisciplinary input from mechanical, civil, structural, aerospace, naval architecture, chemical engineering, electrical, electronics, applied mechanics. It's a multidisciplinary program. You will find this program is completely different, dedicated to industrial training and thorough capacity building on the new trade of maritime sector. It's a grooming economy which will give you a lot of job opportunities and research frontiers as far as India is growing. And the Blue Corridor effect, which is planned by Government of India, is one of the important mission which requires maritime engineering growth to happen in the country. So this program caters to expected that capacity building in this program.
Friends, this is part of a material science engineering laboratory which becomes one of the teaching aid for the maritime engineering program. So when you talk about materials innovation in maritime industry, though concrete and steel have been conventional candidates of choice for engineers, for example, we have titanium vessels, high-speed craft boats made of fiberglass. These are all advanced materials which actually do not come across conventional standard design code of practices. We conduct box furnace test, tube furnace test, vacuum arc melting, induction melting, vacuum induction melting, vacuum sealing unit, which are all present in this laboratory is a small segment of material science laboratory. Friends, a typical furnace where the operating temperature for testing specimen can go as high as 12 degrees Celsius. Generally at room temperatures and ambient condition, the mechanical properties will not alter much. As you see in the course lectures, you will notice that strength of the material get degraded when the temperature rises beyond 600. Therefore, when you talk about fire resistant design, you must also choose an alloying element such a manner that the strength doesn't degrade beyond 600 degrees Celsius at all. Welcome to the ambience of IIT Gandhinagar Lecture Theatre. This is one of the interesting classrooms where the maritime engineering classes will be conducted. We have got state-of-the-art projection facility and good audio-visual recording systems. Once the lecture is over, you see the system here. We can generate the PDF files of the lecture directly and you can email the PDF files directly to your email IDs. So it's a state-of-the-art facility we have in IIT Gandhinagar where the lectures are lifetime recorded and shared with the students immediately. This is the IIT Gandhinagar library. This has got all collections of books which are referred as the standard textbooks and references for the course and the program. It also has lot of online editions of design code of practices and reference materials and e-collections of various video lectures of international courses and programs related to maritime engineering. We will be taking you around to the advanced material manufacturing units. So you will have state-of-the-art facilities available at IIT Gandhinagar. So welcome to the program to join MTech and PhD at IIT Gandhinagar Maritime Engineering. So please try to enjoy and take the advantage of this to the maximum. Welcome to the program and welcome to IIT Gandhinagar. Welcome friends to the SwayamPrabha course titled Maritime Structures offered by Department of Maritime Engineering at IIT Gandhinagar. The program of Maritime Engineering is professionally supported by various universities in the lead role located different parts of the world. It is first of its kind in the country and IIT Gandhinagar is proud to host this program with support of industries and academia in India as well as in abroad. The program is essentially a professionally oriented, specialized design program for maritime engineers, which is totally multidisciplinary. Therefore, the courses what we run under this program of MTech and PhD offered at IIT Gandhinagar will invoke registration from different engineering disciplines as civil, structural, mechanical, electrical, electronics, naval architecture, material science, even chemical, environmental engineering and so on. Therefore, friends, we are making the best effort to make people understand the course contents. So, sometimes certain basic things are repeatedly explained only for the benefit of the viewers. So, if you have a prior knowledge on these segments, it will be advantageous for you to reinforce your learning further and stronger. However, for completion's sake, you will note that many of our lectures are focused on fundamentals, explaining them to multidisciplinary audience. Therefore, sometimes you may feel there are certain things which are overemphasized, which you already know, does not matter. So, now we are on the 38th lecture, friends. Welcome to lecture 38, where we are going to discuss about the stress concentration factor. In the previous lectures and design examples, we understood how to design a tubular member, how to design a tubular connection. Now, how to assess this connection and a special kind of reversal of loadings which induces fatigue in this. As we said in the beginning, in the earlier lectures as well, the stress concentration is a very important botheration in connections of tubular members, which are the weakest segments in the whole construction scenario of maritime, especially offshore steel structures. So, how to assess this connections condition and structural fitness is what we are going to discuss in this lecture. So, welcome to lecture 38, where we will elaborate discussion on stress concentration factor. First, let us start with what do we understand by the stress concentration factor. We know in maritime structures, especially steel, most of the connections are welded. Friends, there is another point I want to discuss with you. You will see that I am actually enabling the blackboard teaching by using a whiteboard and writing it on the board. There are two reasons for this, friends. I could also present this in a PPT form where I can do this lecture much faster. I intentionally do not do it because as I keep on writing on the board, you will follow letter by letter, phrase by phrase, and you will also write them on your notes. So, we want to create an atmosphere where a classroom teaching is happening, though the teaching is virtual. So, please bear with me for my handwriting or any errors there, but however, the intention is that I want to take you to the real classroom, online of course, virtual, so that you follow all the points, all the phrases, all equations line by line, step by step, so that you write once on your notes, refer this further to design codes, you will have a good grip of the basics as well as application of these equations for any kind of problem. The intention is that. So, please follow this in a true spirit and try to also write down these on your notes as you parallelly see, listen and understand these lectures. Okay, most of the connections in offshore steel structures essentially are welded connections. When you have a welded connection, the stress is generally concentrated. A weld has got two components which are primary there. One is the toe of the weld, other is the notch of the weld. These two parts or subcomponents of a weld connection are the most critical ones. So, the concentration of stress happens either in the toe or in the notch. As you have seen in the previous example, the braces connected to cords on different directions in a different plane induces braces connected to the cord induces or let us say imposes out of plane bending, in plane bending and of course axial stresses, maybe compression, maybe tension. So, combination always makes the system more critical. We have seen them in the previous example when we start discussing the design of tubular members as well as connections. So, when we have a combination of these forces acting on a connection, we would check the unity check of these connections under biaxial bending, etc. But then how do we assess this at the joint? Therefore, you will notice that under given wave directions or under reversal of wave and wind directions, these stresses can be reversed. A compression phase can now receive a tension phase and vice versa, because the wave direction is a geographically controlled phenomena. Though we design the system for all direction possible on a given C state and C condition, but still the wave directionality is not under the control of the designer. So, the worry is this induces reversal of stresses. When you have reversal of stresses, then the first thing which comes in mind is first the strength of the joint gets reduced. You know, it is very simple. You have a thick wire. If you try to pull the wire apart, you will not be able to break the wire easily. The easiest way to break the wire is keep on bending the wire up and down. Like you have a wire, you have to bend the wire up and down repeatedly. You will notice that after n number of cycles, the section where you are holding the finger becomes weaker and you can break the wire. So, it is very simple, friends. When you have a member subjected to reversal of loading or forces, the member gets weakened. It means it loses its strength at first place. Second, this phenomena, as we all know from engineering, is fatigue. Now, fatigue is a very special problem. Fatigue is a special problem because of two reasons. One, it induces reversal of stresses, which means that the member should be checked for both nature of stresses. What do you mean by this? For example, if you design the member for tension, you should also check the member for compression. But you have seen the design philosophy and phenomena and the design modalities and failure modes are different when they are in tension and compression, especially when they are caused by bending, which is in plane and out of plane, then the complexity doubles. So, that is the first problem what we have with fatigue. It induces reversal of stresses. The second issue which is very bothering is that fatigue induces failure at a stress level which is very low compared to its yield strength. So far we have been thinking in the design that yield strength is the criteria with which or at which the structure or the member will fail. So, to account for factor of safety, international codes say do not stress the member or the material to its yield value, use a factor of safety, let us say 0.8 Fy you can use. So, 0.2, 20% Fy is taken as factor of safety. So, still the comparison or the borderline is a yield strength. That is what we have been thinking. Whereas, when you have a member under reversal of stresses, the stress magnitude at which this will fail will be much lesser than the yield strength. Of course, this depends on the stress range and the number of cycles, what we call as SN property. So, friends, when we talk about fatigue design, which is of course not a part of this course, but there are other courses in maritime engineering where you can detail understand about fatigue design with MATLAB programs and software support. However, for the interest of all the viewers, we will just touch upon very quickly. In fatigue design, we generally use a philosophy called SN curve. S stands for stress range and N stands for the number of cycles. Okay. So, as the number of cycles keep on increasing, the stress range expected to come down. So, if a typical curve may looks like this, if this is my number of cycle, the stress range for larger number of cycles, the acceptable stress range at which failure occurs will come down. Okay, that is a usual property of any metal, right. So, now the question is, though we will know or we will be able to count the number of cycles for failure, but what stress range will it take in the connection? Now, one may ask me a question, why there is a problem here? We already know the axial stresses, we know the bending stresses, we know their combination, fine. The problem is, see here, if I have a cord member, it is connected to a brace member, okay. When the member is subjected to any direction of forces, okay, you will notice that this will start opening up for this direction. So, the nature of stress induced at this weld point is different from this weld, am I right? So, therefore, in a cord, if multiple braces are connected in different directions, cord will be subjected to different kinds of forces along the connection points. We call them as saddles or saddle points and crown points. So, we call them as saddle points and crown points. You know, saddle and a crown is related to horse seat. Okay? A horse seat looks like this typically. This is a saddle, means a crown. Okay? A typical, a saddle point, a crown point. It means at different locations along the periphery of the connection in a cord at different directions, the cord will receive out of plane bending and in plane bending actions because of the forces and the moments induced by the braces. In addition to that, they will also have different stress concentrations at different points like saddle and crown points or heel and tip or heel and toe, let us say heel and toe of the weld connected to the cord. So, when I am going to talk about the stress concentration or there is a stress range, what stress will I account for? Will I account for the stress at the heel or at the toe, or will I account for the stress at brace 1 or brace 2? So, a big issue comes. Therefore, there has got to be an equation, a methodology, a definition which can account for all these stresses acting on the cord to assess the structural fitness of the cord for the given kind of load. So, this is what in general we call as stress concentration. Stress is getting concentrated. So, therefore, friends, if you look at the detailed analysis, of a joint, I am talking about the welded joints only, okay, of a joint, leads to using S-N curve approach to perform fatigue analysis. As I said in the beginning, this particular lecture will not introduce you to the S-N curve approach of fatigue design. There are other courses where you can learn from this in maritime sector. However, for the knowledge sake, I will definitely request the viewers to understand and have an idea about SN design approach of fatigue design. Please do this. Okay? Let us say the analysis of a joint leads to SN curve approach to perform fatigue design. Okay? Now, the SN curve approach requires estimating uniform stress range, because you need to have a stress range, uniform stress range, it is also necessary to normalize, understand, to normalize, okay, these stresses at the weld junction, is it not? Because one where it is saddle, one is a crown, one is having outer plane bending, one has in plane bending and so on, all are affecting the chord. So, there has got to be a normalized stress value of these stress concentrated at the weld joint. So, we call this as hot spot stress. Range. Shortly, we will refer to this as HHSR, okay, hot spot stress range. So, therefore, friends, as we now understand, stresses at the toe and crown of a weld connection or a weld junction vary. Okay. Why they are very serious? Because chord is considered as a thin shell element. As a thin shell element. Okay, that is how it is resulting in weld ovalization, which we discussed in the previous lectures. Okay. So, therefore, friends, extrapolation of these stresses to the mid surface generally estimates stresses wrongly. Then what should we do? We should use something called stress concentration factor. Therefore, courts recommend use something called stress concentration factor. So, friends, there are two factors here which we are discussing. One is the stress concentration factor, other is hot spot stress range. Let us clarify this once again. For a fatigue design, we need SN curve. S requires stress range, and that is coming from hot spot stress range. However, this hot spot stress range should be a function of stress which is obtained from stress concentration factor, because we are modeling chord elements as thin shell elements. We cannot extrapolate the stresses on its surface to the center, it can be wrong. Okay? So, therefore, there has got to be a connection established between the hot spot stress ranges with the stress concentration, which now accounts for the stresses occurring all along the periphery of the weld at different points of interest from different points of base connections on the same chord. So, stress concentration is a multiple factor which accounts for different effects coming from different braces subjected to in plane out plane bending at the same chord at different locations. So, once I have the stress concentration factors established for different connection points, using that I will try to find out the hot spot stress range. Once I have that range, we know the number of cycles which is reversingly happening. I can use the SN curve approach to estimate the fatigue life of this connection. And we said fatigue life is very important because fatigue is a phenomena where the joint fails at a stress intensity much lower than the yield strength of the material. So, we need to estimate this, that is the idea. I think this preliminary discussion to make you clear about the stress concentration factor and hot spot stress range will be helpful for you to follow the further points. Okay. Now, friends, the stress concentration factor over a wide range of nominal stresses can be given like this. So, the stress concentration refers to the increased stress at a specific location in a connection between the parts of the structure which may occur due to any one of the following reasons. It can be due to geometric change in the load path, it can be local welding profile effects. Okay. The stress concentration factor is given by a simple equation, hot spot stress by nominal stress. Okay. Now, the hot spot stress, so it is a factor, both are stress units, it is a factor, both are stress units, therefore, it is a factor. I multiply this factor with different stresses occurring at different nodes, then I will get the hot spot stress range at that location. Okay. So, a stress concentration factor can be evaluated by any one of the following methods. You can conduct experiments on scaled models using steel and then measure strains and compute the stress concentration. You can also do experimental stress analysis using acrylic material and use photoelastic methods to compute the stress concentration. Thirdly, one can also perform detailed finite element analysis using thick or thin shell elements to compute the stress concentration factors. However, based on experiments on scale and 1:1 models, researchers have identified certain factors on empirical content of certain parameters which are all given for the ready-made use in the international codes of practice. So, which we will now discuss. Remember, these equations are parametric in nature. Whenever we have any parametric equation in nature, the range of these parameters play a very vital role. So, one has got to check whether my problem is within the parameter range or not. If not, I cannot use these equations because these equations are confined only to those parameters identified to be critical, and within that parameters there is a range. Okay? So, these are all empirical equations developed based on detailed experimental studies conducted at different parts of the world and assembled for our information, so that as a design office I can easily use these equations to check the structural fit of any connection with a welded connection. Okay. So, now Epifemio has given certain stress equations, concentration equations and their applicability. They are available in AP-RP2A, which I would urge you to look into the latest revision of the code and look at these equations. However, I will not assume that you will know these equations. I will present these equations on the screen, I will write them and explain them. However, for the correctness and update, please refer to the International Design Code so that you follow the correct equation with the correct commentary of the code. Okay? So, this is only an application exercise done for you to understand. So, what are the different parameters based on which these equations are developed? These are the parameters. Okay? There are some parameters as you see on the screen, alpha, beta, gamma, theta, tau and g by d. They have a lower and upper limit. As I said, the ranges of these parameters are very important, friends. We cannot violate these ranges because the experiments are conducted by varying these parameters and keeping them within these ranges only. However, the results may vary significantly when you have got a problem where the parameters or any one of them are on the border of these values. Okay, when they are on the border, then the behavior may slightly vary. Therefore, there may be disagreements in the real time scenario and the suggested equations by Epiphemio on the stress concentration equations. However, since we do not have access to a large number of data on experimental studies conducted by the literature, we believe that these equations given by the International Codes of Practice for Design are okay and we can use them. Most of the design equations are comfortably done and they are fairly accurate and they will predict always a safe value. Okay? So, these are the parameters, these are the ranges. So, we now understood the importance of these parameters and the ranges and the values, of course, it has been given here. And I reiterate that when you have got any parameter, any two of them or any three of them on the range of the border, then the behavior of the joint can be different from what is predicted by this code. Okay? Right. Now, let us move on to hotspot stress range from stress concentration factor. I think there are two different things. I made it clear in the beginning. There are two different things. Okay? Stress concentration factor is depending on the stress applicable at the connection. The connection has got many braces connected. Even at the brace, there are toe and crown. So, there are many braces, it may cause in plane bending, out of plane bending depending upon the inclination of the brace to the crown, to the cord. Therefore, combining all these effects, we find out stress concentration factor. Once we have the stress concentration factor, based on that, we try to find out the hotspot stress ranges. So, hotspot stress ranges as advised by the code are available here. Let us say, please pay attention to this figure. This is a cord. Okay? This is a cord in plan. The cord has got a center line where the load path transfer is happening. Cord is also subjected to axial loads. Yes, cord is a member which is taking the load from the deck and passing on the load and also receives loads from the braces and passing on the entire load to the foundation. So, cord also receives axial stress, it also receives bending in plane, out of plane. We know this, we already did a design and we checked whether unity check is applicable. We found in our example they found to be safe. Okay? So, cord has got a CG line where the line of action. Circumferentially along this line, we can take many points of our interest. Okay? Let us say from the point where the brace is connected, okay, this is what we call as the crown point and this is what we call as a saddle point. Okay? When the brace is connected to the cord, crown point, saddle point, right? On the cord, circumferentially in plan, okay, T refers to top and bottom. I mean, this is plan, friends. Okay? Top and bottom, or this can be even in elevation where the top and bottom. Then one can also have these 2 points on the left and right of the connection, LR. So, top bottom, left right. Then we can also have top right, top left, bottom right, bottom left. Why are we interested in these kind of 8 points on a cord? 1, 2, 3, 4, 6, 8. There are 8 points. Why are we interested in these 8 points? Okay, let us come to here. Let us first see what are these points of interest for us. SA refers to saddle point, which are L and R position. So, these are the points where saddles are connected. Okay, saddle point, these are saddle points. CR are the crown points, which are actually B and T. These are the crown points. So, crown is the point where brace touches the cord, saddle is the point where brace penetrates to the cord slightly inside. Okay. So, these are L and R are the saddle points, T and B are the crown points. Sorry, B and T are also the saddle points. Okay. Then QR are the quarter points. So, I think there is an error here. Okay. So, L and R are the saddle points, B and T are the crown points. Okay. These are the crown, this is not saddle, this is crown point. I will correct it here. better I write it here. These are the crown points. So, CR refers to crown, okay, crown points. Then let us also talk about the other quarter positions which are BL, BR, that is these points, BL, BR, then BT, BT and TR, okay, the 4 other points, quarter points, right, the 4 other points, 1, 2, 3, 4. So, now we have got 8 points. These 2 are crown points, these 2 are saddle points, these will receive depending upon the connection nature. So, 8 points, okay. So, these are the interpolated points which we have taken for our connection. So, now this will be subjected to axial forces, in plane bending, out of plane bending. So, using this notation, we also have the effect of stresses in the cord only, the crown, at the crown on the cord only is called CE. Depending on this, we try to find out the hot spot stress range at saddle, at quarter and crown using this equation. I can find the hot spot stress range of the cord at saddle, at crown and quarter. Remember friends, to find out that I need stress concentration factor at saddle for axial load, stress concentration factor at saddle for out of plane bending. Okay, that is very interesting. See here, at the saddle points, when the system is moving, they will have out of plane bending, okay, they will move out of the plane of the cord. When you talk about the crown point, you need to find out the stress concentration factor at the crown point under axial loading, then stress concentration factor at the crown point with in plane bending. So, these points will have in plane bending, L and R saddle points. So, these points will have out of plane bending and these 2 points will have in plane bending. In addition to that, you also have a factor CE, which is the effect of stresses in the cord only for the cord crown, only for the cord crown. So, these are hot spot ranges to be evaluated at 8 points on the, these are all for the cord, okay, these are all for the cord, okay. Similarly, for any quarter point like 1, 2, 3, 4, any quarter point here, one can work out stress concentration factors under axial, under in plane, out of plane, because this will be subjected to both in plane and out of plane as the case may be. Okay. So, friends, the hot spot stress ranges at saddle and crown are known to us. Hot spot stress ranges at saddle and crown are known to us. Okay. Saddle, out of plane bending, crown, in plane bending. We can also find for our interest hot spot stress range at quarter points. So, now the question comes, how do we compute the stress concentration factor at the saddle and at the crown for axial, out of plane, in plane bending? If I have these equations with me, I can always find out the hot spot stress range at the saddle point and the crown point using these equations. Once I get the stress range, I can use SN curve approach to find the structural fit of this cord brace connection under fatigue loading. Okay. So, friends, it is very important that when you talk about the crown, we include some effect called CE. Let us talk about what is the CE. CE is actually the effect of cyclic stresses in the cord which is inclusive of cord stress accounting for the impact caused by the waves. Friends, important is here the stress concentration coming from the connectors like braces are accounted, whereas a cord can also have the impact loading caused by the waves directly on the members. So, that is accounted here for the cord. Okay, it is done only for the cord and the crown point. But the saddle point, this problem is not very serious. Saddle is the point where it is penetrated inside this, and crown are the points where the brace is touching the skin of the cord. Okay. As I said in the beginning, friends, the stress concentration factors are given by Epiphanios equation, which are parametric dependent. Let me write down that here. The Epiphanios equation are parametric dependent and they are valid only for certain range of these parameters. So, it is very important, friends, that we realize these parameter values and the ranges and we check these in our design first. Okay, we cannot violate this. And furthermore, if the parameter values are on the border of these ranges, then the behavior is completely or maybe different from what is predicted by the code. Okay. If you have parameters, if parameters fall outside the permissible range, let us say, then stress concentration factor should be computed using the actual values of geometric parameters Which are these parameters? Let us see. First is beta, which is a ratio of d by d. We know what is d and what is capital D. D is small d refers to the brace and capital D refers to the cord, and cord diameter is generally greater than the brace diameter. The permissible range is from 0.2 to 1.0. The next parameter is gamma, which is d by 2t, and the permissible d is the diameter of the cord and t is the thickness of the cord. So, gamma is actually associated to cord only, and the permissible range in this case is 8 to 32. The next parameter is tau, which is the ratio of thickness of the brace to the cord, and the range is from 0.2 to 1.0. The fourth parameter is zeta, which is G by D, where G is the gap. Usually the minimum gap between the successive connections of braces is 50 millimeters. So, and the permissible range in this case is minus 0.6 beta by sin theta to 1.0. That is the range of zeta. And alpha, the other parameter alpha is 2L by D, and the range is 4 to 40, where L is the effective length of the cord. What is effective length of the cord? For example, in plan, let us say I have a cord the load line, okay, and in elevation let us look at this. I connect two braces. So, these are the crown points and the saddle point. This is one brace. I connect one more brace at a different angle. Right. Now, when the connection happens, when the line of load transfer happens, okay, where this is my G and the outer is D and this is small d and this is capital T and this is small t and so on, the effect of this on the cord will not be for the entire length of the cord. There is certain length up to which this connection will influence the cord behavior. We call this as effective length of the cord. Okay. Now, when we talk about theta, theta also has a limit. Theta, the permissible range of theta is from 20 degrees to 90 degrees. You cannot have a brace connected to the cord lesser than 20 degree and of course, more than 90 it will be on the other side, okay, and so on. So, friends, so parameters are seen, stress range is understood, stress range, hot spot stress range depends on stress concentration factor. Now, stress concentration factor is empirical based on parameters. Now, we need to know the equations for finding out these stress concentration factors for different geometric connections like T joint, Y joint, X joint, K joint and so on, which we will refer to the famous equations or the design codes and learn them, and then we will do a design example. So, friends, as a summary, in this lecture, we learned why a connection need to be tested for structural fit, because we understood that a welded connection undergoes fatigue failure easily because there are reversal of stresses possible. When reversal of stress is possible, the connection will fail in a stress which is much lesser than the yield value of the material, because it does not depend on the magnitude, but depends on number of cycles. So, we do this using what is called S-N curve approach, which is more popular and commonly accepted in maritime engineering. So, S-N curve approach needs a stress range. So, stress range is then called as hot spot stress range in our domain of interest and knowledge. So, hot spot stress range is a function of stress concentration factor. Why stress concentration? Because braces are connected to the cord in different directions and different planes, which can cause in plane out of plane bending along from axial stresses. Therefore, stress concentration factor should be computed based on certain parameters. So, these parameters will govern now the SCF factors based on which I can compute HSR, which we will discuss in the next lecture. Hope you have followed the lecture and try to learn them thoroughly. Thank you very much. Namaste.